So continuing on with 9.8 and a little bit of what we're going to talk about in section 10, we will be asked on the AP free response to either take derivatives or integrals of a power series. And we actually did this on our 9.7 worksheet. Let me see, is that this one? Yeah, I'm going to go back to that real quick. Remember this question. G was the integral of f of t. Write the third degree Taylor polynomial for G. So that was me taking the integral of each term I had for the power series from part A until I got something third degree. So anyway, so we're going to be doing that today and talking about, again, intervals of convergence. So same idea with the power series. If we have some sort of power series where you can generate out the terms like this, and that power series has a radius of convergence, something bigger than 0, so it converges somewhere other than just its center point. Then on that interval of convergence, which is just the center plus or minus r, f is differentiable, and if something's differentiable, we know it's continuous. And also, f prime x would be equal to, but you know what, instead of writing this out, because I think that's going to be more complicated, I think I'd rather say this in words. My PDF key has like me taking derivatives of each of these terms, but I'm just going to say f prime x would equal derivatives of each term in the f of x power series. Since they're all going to be some sort of polynomial term, you're just using the power rule here. It's nice and easy. Maybe a little chain rule depending on what your x minus c is. And then the integral of f of x dx would be integrating. Get right today, I'm sorry. Integral of each term in the f of x power series. And again, you would just be using, I think of this still as the power rule for integration. All right, so if you want the formal thing for that, it would, we'd be writing out the terms and taking derivatives, but okay, so what does that mean? Prove using your power series approximations that the derivative of e to the x dx is equal to e to the x. One note I want to make up here, sorry. The radius of convergence stays the same. So if you had a radius of convergence of 1, it'll still be 1 for the derivatives or the integral, but endpoints on interval may change. This just means that when you take the derivative or the integral of a power series, you have to check the endpoints again. Because even if, say, we, in the previous day's notes, the last example, we didn't include 0 and we did include 2 in the interval of convergence, maybe when we take derivatives, it'll turn out that we can't include 0 or 2. Or all of a sudden we can include 0 and 2 or some other combination. Okay, so prove using your power series approximations that the derivative of e to the x is e to the x. Let's start by remembering what our e to the x power series is. What is e to the x again? Okay, we need to have this memorized. Maybe you have the terms memorized. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. It's important to know the nth term of that, x to the n over n factorial. Now let's go ahead and just write that as a power series. So it's the sum from 0 to infinity of x to the n over n factorial. Right? You can check that. If you plug in 0 x to the 0 over 0 factorial. Remember, 0 factorial is 1. So that's where that constant term comes from. Plus x to the first over 1 factorial, et cetera, et cetera. Okay, so here's e to the x. Now, the derivative of e to the x with respect to x, you can think of this as taking derivatives of each of these terms, right? So, okay, the 1 goes away, x becomes 1. X squared over 2 factorial becomes 2x over 2 factorial. 3x squared over 3 factorial. I'm going to do another one. The next term would have been 4x cubed over 4 factorial. The general term would have been n times x to the n minus 1 over n factorial. Well, those all simplify, right? That's 1 plus 2 over 2 factorial just leaves me with x. 3 over 3 factorial, 3 cancels out. 3 factorial is the same as 3 times 2 factorial. So that's back to plus x squared over 2 factorial. Let's do one more. 4 and 4 factorial, the 4 and the 4 cancel out, and you're left with x cubed over 3 factorial. It's looking an awful lot like our original power series for e to the x. N over n factorial does cancel out. I have x to the n minus 1 over n minus 1 factorial. Okay, what would this look like if I didn't just write out a bunch of terms? What if I had it in terms of its power series? So I could say, all right, I can do all of this. Oops, can't talk and write today, sorry. I can do all of this without really having to write out the terms. I'm showing the terms because we're so used to taking derivatives like that. But what if I just had the power series to look at? I should be able to say, well, that's going to be the sum from 0 to infinity of n times x to the n minus 1. I'm just using the power rule on that over n factorial. And I can simplify that if I want to. The n over the n factorial will become n minus 1 factorial, right? But that's the same thing. It gave me that general term. All right. And then instead of starting at n equals 0, I could say, well, start that at n equals 1, and you end up getting the same exact thing. All right, what about example 2? F of x is equal to the sum from 1 to infinity of x to the n over n, which makes it x plus x squared over 2 plus x cubed over 3. All right, so we're not saying this is sine x or e to the x or 1 over 1 minus x or any of that. We're just told find the interval of convergence for each of the following. All right, so just for f of x itself, this is what we did yesterday. How do I figure out this interval of convergence? Since it's not just x to the n by itself, there's a divided by n here. We should use the root test, or I'm sorry, the ratio test. The limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 times n over x to the n. What does that come out to? That simplifies a little bit. N over n plus 1 times x to the first. When I take the limit as n approaches infinity, this rational expression becomes 1. This just equals absolute value of x. As long as absolute value of x is less than 1, this will converge. This power series will converge by the ratio test. All right, so that tells me that negative 1 needs to be less than x, which is less than 1. That tells me that the radius of convergence is 1. This asks for the interval, though. So remember, we need to check the endpoints. So if I check the endpoints, I'm saying, what happens when I plug in negative 1 back into the original series? I get negative 1 to the n over n. That's an alternating harmonic series, which converges. So I'm going to include negative 1. What happens if I put in positive 1? I get 1 to the n, which is just 1 over n. That's the harmonic series not alternating, so that diverges. So the interval of convergence is including negative 1 up to 1, but not including 1. Now, what if I want to take the integral of f of x dx? All right, so how do I do that? I can think about the terms, but I don't really want to have to write out a bunch of terms, so I want to work with just the series. Let's come up with the power series for that. We're going from 1 to infinity. And this is a power rule thing, right? For integrals. I take whatever the exponent is, I add 1 to it, and I divide by that new plus 1 exponent. So this would become x to the n plus 1 over, there's already an n down there, so n times n plus 1. All right. Now you can make that n squared plus n if you want to. I'm just going to leave it like this. And now I need to show what the interval of convergence is for this integral here. So I'm back to using my ratio test to say the limit as n approaches infinity of x to the n plus 2 over n plus 1 times n plus 2, because I plug n plus 1 in here and here, times, I'm going to switch colors so these don't run together here, n times n plus 1 over x to the n plus 1. Let's come down here. Simplify what we have before we take the limit. So I'm going to start with the x's. I've got x to the first, n plus 2 minus n minus 1, x to the first, times n plus 1 over n plus 1, n plus 2. So the x is still there. This is a tie, n squared over n squared. So at infinity, that becomes 1. So again, we're at absolute value of x needs to be less than 1 in order for this series to converge by the ratio test. So once again, I'm looking at x being between -1 and 1, but I have to check the endpoints, plugging them into my new series. So starting at -1, the series goes from 1 to infinity. I've got -1 to the n plus 1 over, I'm just going to make it n squared plus n. Now, this is an alternating series because n plus 1 will alternate between positive and, even and odd values, which makes the terms alternate positive and negative. And I've got alternating, decreasing, continuous from 1 to infinity. So yeah, so this series converges. It's one of those alternating series test series. And then if I plug 1 in for x, so sorry, we're including -1. If I plug 1 in for x, I just get 1 to the n plus 1, so that's nothing. That's 1 over n squared plus n. And remember, this is not a true p series, but it is smaller than a p series, right? 1 over n squared plus n is smaller than 1 over n squared. And I know the series for 1 over n squared converges, which pushes down on that. So this series also converges. Technically, that's by a direct comparison test. So for this one, when I take the integral of f of x, now both endpoints of that series of convergence, both endpoints converge. Now, without having to do the ratio test, remember the interval itself, the radius itself should be the same. It's just the endpoints that change. So I guess I could have gotten straight to the answer, but if this were free response, I'd want to show all of this. But I could have gotten right to the answer and just jumped into the checking the endpoints part. Same thing with this. I should be able just to say, what is the power series for the derivative, and then just check the endpoints. So maybe we'll do it for this one. All right, don't forget, you're going back to the original f of x, that power series. And now we're taking derivatives. So the derivative would be n times x to the n minus 1 over the n was already there. Okay, so those n's cancel out. So this is actually just x to the n minus 1. The sum from 1 to infinity of x to the n minus 1. Now again, to save time on this video, I'm not going to go through, I wouldn't have to do a ratio test anyway. I would just be looking at kind of a simple root or I guess geometric test. But anyway, the only way this has a chance of converging is again if x is between 1 and -1. It's pretty easy to check these endpoints, but again, for free response, you have to show that you're checking. You can't just do it in your head. -1 to the n minus 1 does not pass the nth term test because its terms are not approaching 0. They're bouncing back and forth between 1 and -1. And it is the same thing if you plug 1 in. So those bounce back and forth between 1 and -1, so both diverge by the nth term test. So this interval of convergence doesn't include either endpoint. I guess the only thing I left off of this, let's just go ahead and finish it off. If I just said I'm not going to show all the work. Really, it's just saying by geometric series test. As long as x, which is our radius of convergence, is between -1 and 1, we're good. All right. Now, what if we just use algebra instead of calculus to come up with an interval of, to come up with a power series and figure out its interval of convergence? So we're not taking derivatives or integrals, but we're kind of building a series. So I know a Maclaurin series for sine x. I don't necessarily have one for x squared. But let's think about this. We do know sine x. This is one we're supposed to have memorized, right? It's x, it's all the odd powers. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Just going to do another one. X to the 7th over 7 factorial plus, give the general term. So remember, how does this go? It's -1 to the, how do we express an odd number? Now I can't remember how I wrote this in the other notes. I'm going to leave that off for a minute. X to the 2n plus 1, right, over 2n plus 1 factorial. I almost wrote this as -1 to the 2n plus 1, but I don't need that to be odd, right? This is just -1 to the n if we're saying that n starts at 0, 1, 2, etc. Right? And that is what we're saying, because each term, this is like 2 times 1 plus 1 factorial, 2 times 2 plus 1 factorial. So this does start at 0. Okay, so anyway, that's the sine x. That's the sine x power series. And if I wanted to write that as a power series, it would be the sum from 0 to infinity of that general term I just wrote out. -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And we mentioned this in yesterday's notes. Its interval of convergence. Remember we said if we could add an infinite number of terms, then this power series would match sine exactly. So it is all real numbers. What about sine of x squared? That's what we're supposed to be finding. All you have to do is plug x squared into the sine x function, right? So that's what we mean by using algebra, just using function notation, basically. So x squared minus x squared to the 3rd over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. In general, it would be x squared to the 2n plus 1 over 2n plus 1 factorial. More generally, it would be the sum from 0 to infinity, -1 to the n. Let's clean this up. Instead of x squared to the 2n plus 1, that's now x to the 4n plus 2. Still over 2n plus 1 factorial. And since I've only used algebra, no calculus, no derivatives or integrals happening, this still would converge for all values of x. Okay, so that's kind of nice. Let's do one with cosine. So first we need to know what is our power series for cosine x. Cosine x, maybe you have to write out the terms first. It does not start at, it doesn't start with the odd powers, right? It starts at 1. So we've got 1 minus x squared over 2 factorial plus x to the 4th, 4 factorial. I'll just do one more. Minus x to the 6th over 6 factorial. What's the general term here? Again, they're alternating. Remember, this is n equals 0, 1, 2, 3. So it's negative 1 to the n, x to the 2n over 2n factorial. I kind of think of it as like cosine is the easier nth term, like it has less to it, doesn't have the plus 1 in there. And I think of that as like cosine's alphabetical. Cosine comes before sine, so the easier one comes before the harder one. If that helps you at all, please use that. What's its actual power series? Instead of writing out all the terms, I could just say it's the sum from 0 to infinity of negative 1 to the n, x to the 2n, over 2n factorial. So if I want to build cosine of square root of x, that does just mean you're plugging square root of x into each of these terms. Square root of x to the second power over 2 factorial minus, maybe it would be helpful to write it as x to the 1/2 to the 4th over 4 factorial, etc. Okay, let's just get right to the series though. What's this going to be? You don't need to write out all of the terms. I'm just showing what happens. So the negative 1 to the n isn't affected by that. When I plug an x to the 1/2 and raise it to the 2n power, 1/2 times 2n becomes x to the n. It's still over 2n factorial, right? Because this is going to be x over 2 factorial. This is going to be x squared over 4 factorial. The next one would be x to the 3rd over 6 factorial. So we can see that that's happening. The interval for convergence, for cosine is all real numbers. And since I've only used algebra and plugged values in, no derivatives or integrals taken, the interval of convergence stays the same. What about on this one? I want to find the Maclaurin series for this thing, the integral of sine x minus x all over 4 dx. All right, now there's an integral involved. We're going to have to use calculus, so we will have to check the endpoints. But before we use calculus, let's just build this series before we integrate. Now, I'm not going to write sine x again by itself because I already have that up above. I'm going to start. What is sine x minus x? Let's think about that. Where'd it go? Sine x minus x. Here's sine x. If I do sine x and I subtract x from that, that first term would cancel out, but all the other terms would be there, right? So it would start with negative x cubed over 3 factorial. And then plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus etc. What would that nth term be? Now, we still have that nth term would still exist. It would still be negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. But since I subtracted x out, I'm not saying this is n equals 0 anymore. This was the n equals 1 term, n equals 2, n equals 3. So you don't have to rack your brain over what the new nth term would be. You simply have to shift your power series. If I were writing that actual series over, it would start at 1 instead of starting at 0. I'm not going to write the general series. All right, what else are we supposed to do? We're supposed to divide by 4. Sine x minus x divided by 4 is just dividing each of these terms by 4. Negative x to the 3rd over 4 times 3 factorial. plus x to the 5th over 4 times 5 factorial minus x to the 7th over 4 times 7 factorial. Do not simplify those. Who knows what those values are? But you should always write in the general. So negative 1 to the n times x to the 2n plus 1 over 4 times 2n plus 1 factorial plus dot dot dot. So far I've used algebra. So the interval of convergence for sine x minus x is still all real numbers. Well, I don't really have a good place to write this because we're going to need that space. So I'm just gonna write all reals here. Still all real numbers. But now I've got to take the integral of sine x minus x over 4 dx. Remember, taking the integral is just taking the integral of each term. So think about the power rule. We add 1 to our exponent. So now it's x to the 4th. And we divide by that new exponent. I already had a 4 down there. So now this is 16 times 3 factorial. Plus, this becomes x to the 6th over 6 times 4 is 24 times 5 factorial. Minus, this becomes x to the 8th. 8 times 4 is 32. 7 factorial. What's happening in general? Still are alternating. Are we still alternating with our n's though? Let's see. If n is 1, yeah, this first term is still negative. Yes. Okay. So we can say negative 1 to the n. And then what are we doing with our x's? Well, we were taking we were raising x to the 2n plus 1 power plus 1. So now it's 2n plus 2. And we were taking that 2n plus 2 power and putting it down here. There was already a 4 down there. Now there's a 2n plus 2. And now there's a 2n plus 1 factorial. All right, so what is that? 2n plus 2 times 2n plus 1 is just 2n plus 2 factorial. So that general term, what we're saying is, now I'm going to write my power series. From 1 to infinity, and make sure your terms still match when you plug this in. Negative 1 to the n, negative, positive, negative, that checks out. X to the 2n plus 2, starting at 1, you get 4, 2, you get 6, 3, you get 8, that checks out. Over 4 times 2n plus 2 factorial, I'll just write that. 4 times 2n plus 2 factorial, when n is 1, now this takes some thinking, right? When n is 1, I get 4 factorial, but I have 4 times 4 factorial, and I have 16 times 3 factorial. That is 4 times 4 times 3 factorial. So that's checking out too. Whew, okay, is it still all real numbers? That's what we don't know. Now we have to check an interval of convergence. So how do we figure out when the interval of convergence doesn't have endpoints, when it's all real numbers? Well, we just need to make sure that this still converges by the ratio test. So, ratio test for our final answer. What's the limit as n approaches infinity of, remember you're ignoring the alternating piece, x to the 2n plus 2, 2n plus 2 plus 2 will be 2n plus 4 over 4 times 2n plus 2 plus 2, 2n plus 4 factorial times 4 times 2n plus 2 factorial over x to the 2n plus 2. Lots of simplifying to do. 4's cancel out. In the denominator, you're going to have 2n plus 4 times 2n plus 3, but then the 2n plus 2 factorial will cancel. 2n plus 4 minus 2n minus 2 is x squared. All right, now what about this? I'm getting x squared times the integral of 1 over a bottom heavy thing is 0. So I'm getting 0, which is always less than 1. So no matter what I plug in for x, even if it's 500 billion squared, times 0 is going to be 0. So this still has an interval of negative infinity to infinity, because this converges by the ratio test. That's about as extreme as these problems can get, where you have to build the function, and you have to take the integral of it, and you have to do a ratio test to make sure it still converges and check the endpoints. All right, that's it for today. We have homework number 24. Then we'll come back together Thursday, and we are just kind of practicing and reviewing on Thursday. We'll see where we are and how we feel. Remember, today's Wednesday. It's a virtual day. If you need to Google Meet with me live, please do that. Just email me and we'll set up a time. And I do have office hours both Thursday and Friday. So if you're totally lost, you need to be coming into those because we have a quiz on Friday.